To make a smart glove, we need a flex-sensitive resistor. This is a flex sensor, and the magic ingredient of this is some black conductive ink that you can just see there between the white stripes. And the feature of this ink is that as you bend the flex sensor, it stretches, and that means that the ink gets thinner. And the fact that it gets thinner means that its resistance increases. You have to bend it away from these stripes. You have to bend it this way, not the other way. Some of the people on the internet say that you should bend it away from the ink. That's kind of unhelpful if, like mine, you've got some printed letters on the other side and you're wondering which ink you're bending away from. But you bend away from the stripes. I've connected the flex sensor to a resistance meter, and you can see when it's flat, it's giving me about 15 kilo ohms. If I bend it, we get a maximum once it's settled down around about 70 kilo ohms. Let it go again, and it drops back down to about 16k. The microbit can't measure resistance, only voltage. So to measure the voltage across the flex sensor, we need to set up a circuit using another resistor. That's R2 in this diagram. It's 4.7 kilo ohms. The exact number is not important, but something of that kind of region. And what you see at the moment is the sensor's not flexed and it's reading 15 kilo ohms. If we increase the bend of the sensor, the resistance goes up. The voltage, 0.4 volts. If I increase the bend on the sensor, up goes the resistance, 59k now, and the voltage has gone down to 0.2, 0.24. Let's see how far it will go. Maximum flex is about 70 kilo ohms. And we've got 0.2, let's see if I can get it spot on. So there we go, 0.208 volts. If we unflex, the resistance goes down, but the voltage goes back up. If I can get 15, there we go, to 0.786 volts. To set up this circuit for the EduBit board, we make use of the Grove connector block. And here I've connected the resistor to the D1 cable that gets connected to P0 on the microbit and ground. And the sensor needs to go between VCC and D1. Unfortunately, it's not wide enough. So I've connected it to VCC and D2 and used a piece of cable to connect D1 and D2 together. That achieves the same thing. Now all I have to do is plug it into P0 on the EduBit board. Let's program it in MakeCode. Here we are in MakeCode, and it's just a couple of lines really. The first line reads the pin 0 analog value and puts it in a variable called flex sensor value, and then we're going to write that out to the serial bus. That's going to enable us to draw a graph in MakeCode. So I've connected the microbit to the EduBit board, and if you click the Show Data Device button in the bottom left hand corner, you will see this graph, and you can see at the moment it's peaking at 231, and the signal started to drop as I bend the sensor, drop down to 100, maximum bend round about 70, showing 68 on the graph. So I've set a threshold of 150, that's halfway between the two values that we just saw. And what we do is check to see whether we're below that threshold. If we are, we set the green light to on, red light to off. Otherwise, we set the green light back to off and the red light back to on. So the code for the motor looks complicated, but actually it's quite simple and rather clever. We start by reading the value at pin 0, storing that in flex sensor value, and then we want to determine the speed of the motor. Now we know that the flex sensor goes from 230 down to 70, and the motor's speed ranges from 0 to 255. So we use this rather clever map function to map flex sensor value from the flat sensor value of 230 to 70, onto 0 to 255, and we run the motor at that speed. You can use your imagination for all kinds of applications. For the flex sensor glove, we've seen controlling an LED and controlling a motor. In the next video, we're going to look at controlling a robotic hand. I'm a small creator, so a like and a comment really helps.